All right, so we have made it to the fundamental theorem of calculus. It's kind of a big deal. It's the fundamental theorem. So this says this is how we find the definite integral out without having to do that long limit process. It's just kind of how we had the derivative, where we had the long derivative process and then the shortcut rules. Same idea with the integrals. This says if f is continuous on a closed interval and f is an antiderivative of f, then the integral, this is how you say this part right here, the integral from a to b, let me say this part. The integral from a to b of f of x is equal to big F, this would be the antiderivative of b, minus big F of a. So I might link a silly video of some kids singing a song that helps you remember this. But the integral from a to b of f of x is equal to f of b minus f of a. So what does that look like? Well, first, we have to find big F. We have to take the antiderivative. So sometimes students get really confused when they see the 0, 2, and they think, oh no, what am I supposed to do? My advice is pretend like the 0 and 2 are just not there. Like for a second, just pretend like they're not there. And I want you to find the antiderivative like we did a few sections ago of this function. Well, we would multiply it out and say x squared plus x times 1 is x, and then double it, 2x plus 1 squared is 1. We take the antiderivative by the power rule. So this would give us x cubed over 3 plus x squared plus x plus our Charlie plus c. But that's the indefinite interval. Okay, so I actually do have bounds. I have 0 to 2. So after you take the antiderivative, after you do the power rule, you have to take away this summation, this integrand sign, because I don't want to do that again. But if you have bounds, what we do is we put a line over here so we don't forget what our bounds are. We're evaluating this from 0 to 2. So what that means is you're going to plug in, this is like your big F of 2, you're going to plug in 2 for every single x that you see. This is where algebra comes in handy, and this is where students actually end up messing up a lot of times. It's just the algebraic evaluation. Whoops, I need to change my color back. So we have 2 cubed over 3 plus 2 squared plus 2 plus c. That's f of 2. And then we need to subtract f of, that's f of b, f of a, f of 0. Well, I need to put parentheses here. That is a really big important thing, because when you go to subtract, you want to subtract your entire group. But we're plugging in 0, and what happens when I plug in 0 is actually these all 0 out. And so you get 0, you're just going to get minus c. Now you're always going to have this plus c and this minus c, so we don't actually have to write plus c for the definite integral because it will always cancel out. So really we just need to evaluate this. So that would give us 8/3 plus 4 plus 2, so plus 6. Everyone multiplied by 3 over 3, that's 18/3. So 8/3 plus 18/3 gives us 26/3. So that is a much faster way than doing that whole long limit process we did last section. So let's do the next example. So again, we're going to take the antiderivative. These are special rules though. You need to look back at your chart to help you remember the antiderivative of cosine is sine. The antiderivative of 1 over x is natural log of x. Since I took the antiderivative, I evaluated this integrand part. I'm going to write a little, the dx goes away. That lets you know the variable, that's our constant of integration, it's x. That's going to go away. I'm going to write this bar here, and I'm evaluating it from e to e squared. So plug in e squared for both x's, and then plug in e for both x's. Oops, e squared. I didn't even plug in e squared right here. Okay. So sine of e squared, we're just going to keep that sine of e squared, minus natural log and e, they cancel and you get 2. And then we're going to distribute this negative. So minus sine of e, and then plus natural log and e cancel, you're going to get just the exponent, which is 1 here. So I have sine of e squared minus 2 plus 1. I'm going to write minus sine of e, and then if I combine negative 2 and a positive 1, I get negative 1. So this is my answer. And it's okay to leave it like that. E is just a number, 2.7 ... It's like pi. All right, what's the antiderivative of this? Well, we need to rewrite it first. Roots and fractions rewrite. So that would be the square root of 2 over the square root of x squared. What's the square root of x squared? X. So this is like the square root of 2 over x, and we're integrating it from 1 to 8. This function will not exist at 0, but our bounds don't start at 0, so we're okay. Now, the square root of 2 I can just pull out front. The square root of 2 is just a multiple. That's that kx rule. We can pull out the k. And so I'm integrating 1 over x. And what's the antiderivative of 1 over x? That is the natural log of x. So I took the integral, so then the integrand goes away. You put this bar here, and you remember f of b, the top one, minus f of a. So root 2 natural log of 8 minus root 2 natural log of 1. The natural log of 1 is 0. So this is your answer, root 2 log 8. The antiderivative of 3 is 3x. The antiderivative of secant squared is tangent. Oops, 3 theta. Theta is the variable here, so remember that 3 theta plus tangent theta. And I took the antiderivative, so I'm going to put the bar here. Pi over 4 is my a, pi over 3 is my b. So 3 times pi over 3 plus tangent of pi over 3 minus parentheses. It's always important to put that parentheses. 3 times negative pi over 4 and then plus tangent of negative pi over 4. All right, so I have these cancel. I get pi. What's the tangent of pi over 3? Pi over 3 is here, and my x is 1/2. My y is root 3 over 2. Tangent is y over x, so it's root 3 over 2 over 1/2, so it's root 3. This would be plus because of negative 3 and a negative pi, that becomes plus 3 pi over 4. And then minus tangent of negative pi over 4. Well, negative pi over 4 is here. The tangents of the pi's over 4 are 1 in the first and third and negative 1 in the second and fourth quadrant. Tangent is negative 1 here because it's positive root 2 over 2, negative root 2 over 2. Y over x would give you negative 1. But we're doing minus a negative 1, so it actually ends up being plus 1. And if I want to add these, that's like 4 pi over 4. So if I add 4 pi over 4 and 3 pi over 4, that would be 7 pi over 4 plus root 3. And then minus a negative is plus 1. Let's do the next one. Okay, so this problem we have to break up because absolute value function is a piecewise function. It is negative x when x is less than 0. And it's positive x when x is greater than or equal to 0. And we're integrating from negative 1, which is over here, to 2, which is over here, which we could find the area just using triangles, geometry, okay? Or we can split it up and we can say we're going to go from negative 1 to 0 because that's where this pointy turn is. That's where it changes definitions. And we're going to do the work of the absolute value. It's negative x on that side. That's the line. This line right here is y equals negative x. It has a negative slope. So that's what we're integrating on that side. And then plus the integral from 0 to, we're going to be in 2 of positive x dx, because now we're over here. This is the line y equals x. So the antiderivative of negative x is negative x squared over 2 from negative 1 to 0. This would be positive x squared over 2 from 0 to 2. F of b, so plug in your top minus, well, there's a lot of negatives here. Hold on. Minus negative 1 squared over 2. All right, so this is 0. A negative becomes a positive here, and then also negative squared returns a positive. 1 over 2. But you want it to be positive, because if it's not positive, that doesn't make sense because it's absolute value and it's above the x-axis everywhere, so you need to have a positive area for absolute value. So that part's 1/2. Over here, I'm going to plug in 2 squared over 2 minus 0 squared over 2. So I get 2. So I get 1/2 plus 2. So 1/2 plus 4/2, which would give me 5/2, which makes sense. This area is 5/2 because this area would be 1 times 1 divided by 2. So that part is a half. And this area over here is a triangle. 2 times 2 divided by 2 gives you 2. So it makes sense geometrically as well. Find the area bounded by the graphs. So we need to graph this x cubed plus 6x. Let's see, let's factor that out. X, we have with x squared plus 6. So x equals 0 is your only, so x squared plus 6x. I mean, x cubed plus 6x. All right, so it's pretty steep. Very steep. It's kind of hard to draw. It's like, okay, from y equals 0, so that's this line here. And x equals 2 would be a vertical line right here. So we're trying to find this area, which basically is giving us the bounds from 0 to 2. So we want to find the area underneath that curve from 0 to 2. And so we're going to write our integral ourselves. It would be the integral from 0 to 2, x cubed plus 6x dx. Now this one we can't find out with geometry because it's not a perfect line, right? So we have to use calculus, and we can do the shortcut though. We don't have to do the long limit definition. We take the antiderivative of x cubed. Antiderivative is the power rule for integrals. So you add 1, divide by it. And this one would be 6x squared over 2. So 3x squared, and we're evaluating it from 0 to 2. So you're going to have 2 to the 4th over 4 plus 3 times 2 squared minus, you're going to get 0 for both of these. So you don't have to worry about that. So 2 to the 4th is 16 divided by 4 is 4 plus 4 times 3 is 12. So I get 16. That means this area here is 16. So that is that one. I'm going to pause for just a minute. Okay, let's finish this. All right, so this is called the mean theorem for integrals. And it says if f is continuous on a closed interval, then the integral from a to b of f of x is equal to some height c times b minus a. And so this is called the average height of a function. When you solve for the average height, it is 1 over b minus a times the integral from a to b. So what does that mean? I used to give my high school students mini M&Ms, and we had different shapes of graphs. And I told them to fill underneath their graph with all the mini M&Ms. So I want you to just kind of imagine that you had tiny little mini M&Ms that you could accumulate some area. So this is our B. So here's our A, here's our B, and we have this to represent our area. That represents the integral from A to B. And then I say, okay, I want you to rearrange these M&Ms so that they're shaped of a rectangle. So instead of having this curved shape, I want you to push down. So maybe it would be about here. Like these M&Ms could fill in over here, maybe a little bit higher. Those M&Ms would fill in over here. And then this right here is the average value or the average height of the function. It's kind of like you're summing up all of the function, because to find an average, what do? You add up everything and then you divide by the number. And kind of that idea, you're summing up the values and you're dividing by this length of the interval. You're dividing by the width, and that gives you the height, the average height of the function. As far as calculating it, you calculate it just like we did with the fundamental theorem of calculus. You just put 1 over b minus a in front of it. So how do we find the average value? We would say that it's 1 over 3 minus 2, the interval from 1 to 3, 9 over x cubed dx. That's equal to 1 over 1, 9x to the negative 3, rewrite it. So then if I take the antiderivative, so I add 1, that'll be 9x to the negative 2 divided by negative 2. from 1 to 3. And if I rewrite this, this x to the negative 2 is the same as x squared in the denominator. So negative 9 over 2 times 3 squared minus a negative is going to be plus 9 over 2 times 1 squared. 3 squared is 9. So these actually cancel. So it'd be negative 1/2 plus 9/2, which would be 8/2, which would be 4. And then it says to find the c values guaranteed by the mean value theorem for the integral. So then it's asking us to find the values where this happens. So where is this function equal to 4? So if I put 9 over x cubed equal to 4, I get 9 over 4 equals x cubed, and it would be the cube root of 9 over 4. That's where the function actually equals 4. Let's try another one. So same idea, find the average value of the function. So when you see that phrase, you're going to do 1 over b minus a, the integral from a to b of the function. So 1 over, in this case, pi over 3 minus a negative pi over 3, so that's plus pi over 3. The integral from negative pi over 3 to pi over 3 cosine of x. So that's 1 over 2 pi over 3. And then the integral of cosine is sine. We're going to evaluate that from negative pi over 3 to pi over 3. So if I flip this, that'd be 3 over 2 pi. Dividing by a fraction is multiplying by the reciprocal. Sine of pi over 3 minus sine of negative pi over 3. Okay, pi over 3 is right here. The sine value is up a lot, so that is root 3 over 2. And if I go negative pi over 3, the sine value would be negative root 3 over 2. So I have 3 over 2 pi times root 3 over 2 minus a negative root 3 over 2, so plus root 3 over 2. So that would be 2 root 3 over 2, or just root 3. So I have 3 root 3 over 2 pi. That is my average value of this function. And then if I need to find where it's equal, I would set cosine of x equal to 3 root 3 over 2 pi to figure out where it's actually equal to that. And here I would use my calculator. I would put this in y1 and put this in y2 and graph and intersect, or you can just do cosine inverse. You push second cosine to do the inverse. 3 root 3 divided by 2 divided by pi. And I get 0.5971. So you can push cosine inverse 3 root 3 and then make sure you divide by 2 and divide by pi. Or 3 root 3 divided by parentheses 2 pi. You're dividing by the 2 and the pi. And so that is an example there. This is talking about the definite integral again. And the second fundamental theorem of calculus is a subset of the first. And this is special though. This is if I'm taking the derivative of an integral. These are inverse operations. It's like if I said, I want you to take the square root of something that you squared, what do you get back? X. It's kind of like that. I'm taking the derivative of the antiderivative of f, and what do you notice? Does f change? Little f is still little f. It's not big F. You're not taking the antiderivative. You're taking the antiderivative, and then you're taking the derivative, so it goes back to little f. So you're just plugging in whatever this bound is here, x. Now, what happens in part 9, though, is that we need to, I'm going to do a different example first. I don't really love this. Let me pretend like I had 0 to x cosine of t dt, okay? I'm going to do this the long way, and then I'll show you why this formula makes sense. So let's actually find, I'm going to put x squared here. Let's find the integral of cosine. Well, the integral of cosine is sine. And this is my first fundamental theorem of calculus, sine of x squared minus sine of 0. Then I'm going to take the derivative because that's what it says to do. But what's the derivative of sine of x squared? Well, cosine of x squared times the derivative of x squared. There's the chain rule there. Minus the derivative of any constant is 0, because that's already 0. So we have 2x cosine of x squared. So really, I like to write it like this. The derivative from a to g of x of f of t is equal to f of g of x, you plug in g of x, times g prime of x. You have to account for so like times x prime, times the derivative of whatever that is. You have to account for the chain rule because of this situation here. So you don't have to do it the long way. You can just look at this and see, oh wait, I know this function is going to stay the same because I'm taking the derivative of the antiderivative. So I know cosine is going to stay cosine. It's just the bounds, you have to be careful with the bounds. So this answer is still going to be cosine. Cosine of what? Well, cosine of x squared. And then you need to account for the chain rule. You need to multiply by the derivative of this. And if this is a constant, you don't have to worry about it because the derivative of any constant is 0. So that is how to apply that. Let's try it for this example. I'm taking the derivative of the integral. So if I'm taking the derivative of the integral, then write that as t to the -3, or actually you don't have to do that. Okay, well, I'm going to plug x squared in for t. So 1 over x squared cubed. But then you also need to remember to multiply by the derivative of x squared, which is 2x. So this would be 2x over x squared cubed. A power to a power you multiply. So that's x to the 6th. So that would be simplified to 2 over x to the 5th. So that would be the answer of this problem if you're finding the derivative of the antiderivative. So just again, be careful if this bound is not just plain old x. So let me give you a couple more examples of that just so you can. Okay, again, these problems are special because we're taking the derivative of an integral. And so this is when we use the second fundamental theorem, which says plug this into here. Do not change this function because you would integrate it, but then you would differentiate it again. So it would go back to where it started. But then don't forget to multiply by the derivative of this, which is just 1. So it's just sine x. Okay, this one I plug x squared into here. So it'd be the square root of x squared, but then you need to remember to take the derivative of this and multiply it. So 2x times x, so the answer actually would be 2x squared. Plug x cubed in for both of these t's here. So x cubed to the 5th plus x cubed, so that would be and then multiply by the derivative of that, which would be 3x squared. So that just showing you a few other examples. Okay, that's all for that unit. Let me know if you have questions.